Hello students, welcome to EPG Pathshala. I am Dr. P.K. Aluwalia from Physics Department, Himachal Pradesh University, Shimla. Today we are going to discuss about the module Ensemble Theory, Classical Part 1, Concept of Phase Space and its Properties under the paper Statistical Mechanics. So students, let us see what we are going to learn in this module. We shall examine the relationship between an n-particle system and its time evolution in phase space. To recognize phase space as a hyperdimensional space with interesting geometrical properties. Appreciate the significance of phase space as a discrete space consisting of cells each of minimum volume h raised to power 3n as per the Heisenberg's uncertainty principle, where n is the number of particles in the system, and construct phase space trajectory and phase space volume of some interesting physical systems. This module has been developed for postgraduate level as per the following subtopics: degrees of freedom, phase space, visualization of phase space corresponding to phase space of a free particle confined to move along a line, phase space of a simple harmonic oscillator, properties of hyperspace, that is n-dimensional space, distance of a point in n-dimensional hyperspace and consequence of small change in position, volume of a sphere in n-dimensional space, and we will see phase space and its link with quantum mechanics. Workbench of statistical mechanics, phase space. In the microscopic description of a macroscopic system made up of a large number of particles, approximately of the order of 10 raised to the power 23, state of the system at any instant t requires specification of instantaneous position and momentum of each of the constituting particles making the system. This leads us to so-called workbench of statistical mechanics, a kind of a conceptual space where all the action in statistical mechanics happens for its statistical study. Phase space provides us the methodology for counting the number of possible states, that is, the number of microstates, for a given system of interest. In this module, we study this idea leading to a hyperdimensional space of momentum and position coordinate space called phase space. We look at the properties both classically and quantum mechanically of this hyperspace, which shall be useful later in statistical description of the system of interest. The key notions are phase point, phase space, trajectory, and dimensionality. Degrees of freedom. In classical mechanics, degrees of freedom F corresponds to a number of independent parameters needed to completely define position and motion of a mechanical system. Consider a system made up of a single particle allowed to move in all three directions. The state of such a system at any instant can be described by three position coordinates or three momentum coordinates amounting to 3 degrees of freedom. If we constrain this particle to move in a plane, only two position coordinates or two momentum coordinates are needed to describe its state, reducing the number of degrees of freedom to 2. If we further constrain to move the particle along a straight line, one position or one momentum coordinate are needed to describe its state, thereby system having 1 degree of freedom. If a system has n particles, for its complete description, we require 3n position coordinates or 3n momentum coordinates, a total of 6n coordinates. That is, F is equal to 3n. Hyperspace of statistical mechanics, an idea of n-dimensional space. At any given instant, knowledge of degrees of freedom provides us a geometrical way of visualizing state of a mechanical system by means of a space which must have the dimensionality equal to the degrees of freedom of the system. Such a geometrical construct is called a phase space. Each point of the phase space describing a state corresponds to a set of coordinates in 6 n dimensions: q1, q2, q3, so on up to q3n, p1, p2, p3 and so on up to p3n, which is called a phase point. The number of position and momentum coordinates is 2 times the number of degrees of freedom for the system. The number of position and momentum coordinates is 2 times the number of degrees of freedom for the system. As the system evolves with time, state of the system traverses a trajectory in phase space, going from one state of a system to another and so on. Figure 1 describes a constant energy surface in phase space and phase trajectory. This evolution of phase trajectory with time is determined by the Hamilton's equations of motion, which are qi dot, where dot stands for the time derivative, is equal to partial derivative of the Hamiltonian, which is a function of qi and pi with respect to pi, and pi dot is equal to negative of the partial derivative of Hamiltonian with respect to qi, where h, which is the Hamiltonian of the system and has no explicit dependence on time. H is equal to E is the energy of the system. For a free particle system, this amounts to satisfying the condition summation over k is equal to 1 to 3n, pk square upon 2m is equal to E. In general, for an interacting system, this amounts to summation over k is equal to 1 to 3n over pk square upon 2m plus half multiplied by summation over j is equal to 1 to 3n v as a function of qjk is equal to E. From here it is obvious that phase point shall traverse a trajectory on the surface of 3n minus 1 dimensions, satisfying the above condition. This space with 6n dimensionality is also referred to as hyperspace of statistical mechanics, with which we have to deal with while counting the all possible microstates which a typical system can visit. Indeed, a very complex entity with n as large as Avogadro's number. We would like to have visualization of phase space through a few case studies. For visualization of phase space, we must try to identify the region of interest, which decides the volume of the phase space available to the system, which, as we shall see later, ultimately decides the calculation of entropy of the system through an interesting counting procedure. We will, at the moment, focus only on visualization of the phase space of some simple systems, namely one-dimensional motion of a free particle and a simple harmonic oscillator. Phase space of a free particle confined to move along a line. Let a free particle be confined to move along a straight line, say x-axis, of length L with constant energy E. The energy of this particle as it moves over this line is the kinetic energy which it possesses, such that we can write p square upon 2m is equal to E. This implies that for all values of q on the straight line of length L, momentum can have only two values, p is equal to plus minus square root of 2me. This looks like two straight lines parallel to q-axis. This animation shows us the phase space of a free particle confined to move on a straight line. Along the x-axis, we have plotted the position coordinates, and along y-axis, we have taken the momentum coordinates. You can very conveniently observe that the phase space for this free particle corresponds to the two parallel lines drawn parallel to q-axis. Noting once again that for every q along the x-axis, the values of p either lie on p is equal to plus square root of 2me or on the line p is equal to minus square root of 2me. Figure here shows motion of a particle in one dimension confined to move on a straight line of length L is equal to 10 with p lying between p and p plus delta p. This actually represents the phase space of the particle. You observe once again in this figure that the graph in the positive half represents a band of width delta p, and also a band in the negative half represents a band of width delta p. This is the phase space corresponding to motion of a particle whose momentum lies between p and p plus delta p. Phase space of a linear simple harmonic oscillator. The energy E of a one-dimensional harmonic oscillator can be written as E is equal to p square by 2m plus kq square by 2, a well-known result, where p is linear momentum, q is position coordinate, m is the mass of the body executing simple harmonic oscillation in one dimension, and k is the force constant. The parametric form of this equation is given by p is equal to a sine of omega t and q is equal to b cos of omega t, where a is equal to square root of 2me and b is equal to square root of 2e by k and omega is equal to square root of 2mk. You will observe that p upon a is equal to sine of omega t and q upon b is equal to cos of omega t. If you square p upon a and add square of q upon b to it, answer is equal to 1. On simplification, you will find that it leads to once again the result E is equal to p square upon 2m plus k q square upon 2. The adjoining figure shows the phase space of a linear sample harmonic oscillator whose energy lies between E and E plus delta E. Once again, we have plotted in this figure P against Q. The width of the region corresponds to delta E. The region lying between the two ellipses is the phase space region accessible to the particle executing simple harmonic oscillations with energy lying between E and E plus delta E. It is worth exploring properties of this hyperspace, which we have called as phase space. It is worth exploring some of the geometrical properties of this hyperspace, which we shall find useful at later stages while calculating the phase space volume and counting the number of possible states. Distance of a point in n-dimensional hyperspace and consequence of small change in position. Let there be a point x is equal to x1, x2 and so on up to xn. Then the distance of this point from the origin is defined as modulus of x is equal to square root of summation of I is equal to 1 to n xi square. Suppose n is very large number, say Avogadro's number. If sum of xi are not 0, then absolute value of x or modulus of x is proportional to n raised to power half, which is indeed a large number. Furthermore, if each xi changes by a small amount, say delta xi, approximately equal to epsilon, then absolute value of the change in x is proportional to epsilon multiplied by n raised to power half. Interestingly, even if epsilon is small, absolute value of delta x can be large since n is very large, typically of the order of Avogadro's number. Volume of a sphere in n-dimensional space. Let us note that volume of a sphere in 3-dimensional space is given by V is equal to 4 upon 3 pi r cube, and surface area, which is derivative of V with respect to r, is given by 4 pi r square. Obviously, therefore, volume Vn of an n-dimensional sphere of radius r shall be proportional to r raised to power n, and surface area Sn of this sphere is proportional to n r raised to power n minus 1. Thus, Vn is equal to Cn r raised to power n, where Cn is the proportionality constant and can be calculated easily using the value of a Gaussian integral. We know that integral from minus infinity to plus infinity of e raised to power minus x square dx is equal to square root of pi, a well-known result from mathematical physics. This implies that integral of minus infinity to plus infinity dx1 so on up to minus infinity to plus infinity dxn of summation over I is equal to 1 to n e raised to power minus xi square can be written as product over I is equal to 1 to n of the integral minus infinity to infinity dxi e raised to power minus xi square, which is equal to pi raised to power n by 2. Also, in spherical polar coordinates, the above integral can be written as integral from 0 to infinity Sn, where Sn is the surface area of the hypersphere multiplied by dr e raised to power minus r square is equal to 0 to infinity n multiplied by Cn r raised to power minus n minus 1 e raised to power minus r square dr is equal to pi raised to power n by 2. Therefore, if we take NCn out of the integral sign, then integral from 0 to infinity r raised to power n minus 1 e raised to power minus r square dr is equal to pi raised to power n by 2. Making a change of variable r square is equal to y, we can write NCn by 2 integral of 0 to infinity y raised to power n by 2 minus 1 multiplied by e raised to power minus y dy is equal to pi raised to power n by 2. That is, NCn divided by 2 multiplied by gamma function of n upon 2 is equal to pi raised to power n by 2, where we have used a standard result which says that integral from 0 to infinity y raised to power n by 2 minus 1 multiplied by e raised to power minus y dy is equal to gamma n by 2, a standard gamma function. Therefore, Cn is equal to pi raised to power n by 2 divided by n by 2 gamma n by 2 is equal to pi raised to power n by 2 divided by gamma function of n by 2 plus 1. Hence, volume in n-dimensional hyperspace is equal to pi raised to power n by 2 divided by gamma function of n by 2 plus 1 whole multiplied by r raised to power n is equal to pi raised to power n by 2 divided by n by 2 factorial multiplied by r raised to power n. And the surface area of the hypersphere, which is derivative of Vn with respect to r, is then given by Sn is equal to n pi raised to power n by 2 divided by gamma function of n by 2 plus 1 r raised to power n minus 1, which can be further simplified to 2 pi raised to power n by 2 divided by n by 2 minus 1 factorial r raised to power n minus 1. Now we shall look at the link between phase space and quantum mechanics. We have seen that classically phase space is a continuum in hyperspace of 3n position coordinates and 3n momentum coordinates, that is a total of 6n coordinates or degrees of freedom. Each point in the phase space or each set of points q1, q2, so on up to q3n and p1, p2 and so on up to p3n represents the state of a given macroscopic system. And since q's and p's form a continuum, therefore there are infinitely accessible phase points in phase space. However, because of Heisenberg's uncertainty principle in quantum mechanics, which states that a particle cannot occupy a certain volume in coordinate space and certain volume in momentum space simultaneously, this means that there is a minimum volume in phase space within which it is not possible to indicate certainly the state of the system, such that the product of delta p and delta q is of the order of, that is, delta qx multiplied by delta px is greater than equal to h, delta qy multiplied by delta py is greater than equal to h, delta qz multiplied by delta pz is greater than equal to h. In general, this amounts to, for a system of one particle, a minimum volume of phase space equal to h cube, that is, cube of the Planck's constant. If there are n particles in the system, it shall amount to h raised to power 3n volume of phase space. This brings in quantization of the phase space, which has immediate consequence on the counting on probable states for a given state of a microscopic system. This was proposed first of all by Secour and Tetrode independently for the correct enumeration of microscopic states. So students, let us summarize what we have learnt in this module. In this module, we have learnt about the important concept of degrees of freedom for a n-particle system, about the concept of phase space, the workbench of statistical mechanics, and the meaning of dimensionality of phase space, phase point, phase trajectory, and constant energy surface, about how phase trajectory for a system evolves and is determined by Hamilton's equations of motion, how phase trajectory can be visualized in the case of a particle confined to move along a straight line of length L with constant energy E, how much phase space is accessible to a particle executing simple harmonic oscillator with energy lying in the interval E and E plus delta E, how to calculate volume and surface area of a hypersphere in an n-dimensional space, a very useful result in counting the number of probable states available for a given state of a macroscopic system, how in going from classical mechanics to quantum mechanics, we discretize the phase space into cells, with each cell having a minimum volume of h raised to power 3n, guided by Heisenberg's uncertainty principle, which has an important implication of counting the number of probable states in a system. Thank you.